All right, you'll notice that in some of this, there's some extra topics in here that we haven't covered, but you know at this point how to solve any problem related to work and energy. But there are some concepts that we have to connect and make sure you kind of finalize. So these are going to be mostly conceptual, not problem solving things. So we've covered everything you need to know technically, okay? But you'll probably have some terms that I mentioned that are used in textbooks or things like that. Even in College Board, you'll need to understand. They're not special things. They're not anything unique. And I'm just going to connect them to how we explained them before. You should understand the terminology. One is conservation of energy. We've been using conservation of energy a lot, and it's just when the external work is zero. Because if the work is zero, then that implies the change in energy is zero, which means that the final minus the initial energy is zero, which means the final energy just equals the initial energy. And you might have seen me use that sometimes. I do shortcut that a little bit sometimes and just go straight into there. But work being zero is just a special case. Energy is conserved in that scenario. The initial energy and the final energy are the same. And it's just when the external work is zero. So there's nothing special about it, anything different we're going to do. Just when it's a special case when the external work is zero. Then energy doesn't change. It stays the same the entire time. So what's happening is there may be conversions from one form of energy to another, but overall it's staying about the same. Second part, conservative versus non-conservative forces. This is a very technical definition. It actually comes from multivariable calculus, which you guys don't need to know at this point for this class. But there's not a particular reason to know this concept, but this is kind of how the formal definition works. Okay, conservative forces are forces that are path independent. That means the force is always pointing in the same direction of gravity. Our force is where the work done is path independent. Non-conservative forces are where the work done is dependent on the path that it takes. And so why would the path matter? Okay, in practical terms, like for a conservative force, it's always pointing in the same direction, like gravity. Then it's a conservative force. Because what that means is, like, if I go upwards and downwards during the motion, all that matters is the overall displacement. Because the entire time, as we're moving, the force is pointing the same way the entire time. It's always pointing downward the same amount. That means if you think about the total work calculation, all that matters is where I start and where I end. Because the displacement over the time, the force is pretty much constant in direction and magnitude the entire time. That's the most practical way that matters. What about air resistance? Let's say we're taking this path and we talk about air resistance, okay? Or a drag force or something like that. Well, drag forces or friction, or let's maybe you say there's friction instead. Let's talk about frictional force because we don't do a lot of air resistance. But let's talk about a frictional force. So I have a block that's sliding here. And if I slide this way, and then this way, and then this way again, then what's going to happen is as it's moving, the frictional force during this motion, the frictional force is going this way, then it goes this way, while the red arrows are the displacement, and the blue arrows are the direction of the frictional force. Notice that when it slides to the right, the frictional force points to the left. When it goes to the left, the frictional force points to the right. When it goes to the right, the frictional force to the left. So during all three portions of motion, the work is going to be less than zero the whole time. And so that means if I add up the total amount of work, it's going to matter that it's changing directions, because that's going to be more than saying like, oh, I just go straight from there to there. Okay, the work is going to be different, right? Even though if you added them up. Okay, so that's what the practical importance is. It has to do with the fact that if I'm doing like a path with friction, that because the displacement and the direction of the frictional force is changing along with the motion, then it matters which path I take in terms of how much work is done by friction. Whereas gravity, because it's always pointing down, when I go up, we're doing gravity's doing negative work. When I'm doing down, gravity's doing positive work. They somehow cancel each other out because it's the same amount. So all that matters is where I started and where I ended. Okay? Again, not really something you have to know. There are some consequences from this, which I can't derive to you, which again would require multivariable calculus, but it allows you, conservative forces lead you, for those of you later on who lead you to potential energy. For those of you in AP Physics C, this will matter because we have a lesson on general potential energy. But non-conservative forces, you cannot have potential energy. That's a consequence. And again, it's not a super important consequence at this point. Mathematically, it would, but it does matter that non-conservative forces, we don't talk about potential energy of, say, friction, but we do talk about potential energies of, say, springs and gravity. And that's because those are both conservative forces. It is path independent. All that matters is how we got from A to B, or where A is and where B is. It does not matter how we got there. Whereas in conservative forces, it matters. Like I said, for AP Physics 1, this is not a very important thing. For AP Physics C, you can only have potential energy with conservative forces, okay? And so that's why, again, the mathematics are not super necessary. The concepts themselves are not super necessary, actually, other than this portion here, but that's just the general idea. It's not going to factor into any of your problem solvings or understanding, and is not really going to give you much more insight into it, other than at a very theoretical sense, why we have potential energies for certain kinds of forces. Why we don't handle, like, including the surface to talk about the potential energy due to friction. It's because it's a non-conservative force, because it is path dependent. And so we can't use things like the location of it to do it. But again, beyond that, in terms of a practical side of things, it doesn't really matter that you understand the differences between those two, other than if you're going to get asked about them on a test.